great pleasure to introduce Dr. Viv Kendon. She's from physics in the University of Durham, but she's also chair of our sister CCP, which is CCP Quantum Computing. And she's going to tell us a bit about, this is a new CCP, so we're very excited. And obviously we're all going to try and work together as best we can. So she's going to tell us a bit about the state of the art for quantum computing and the prospects for biomolecular simulations and some things about CCP-QC too. So thank you, Viv.
Okay, great, cool. And I should tell you all that we've got Sarah on our management team, so we will always know enough about biosimulation because she'll make sure that we know everything we need to know from your CCP. So we're already practicing working together that way. So we are logoed. You'll see later, we also have Twitter and website. But mostly what I'm going to do with this talk is talk about how we could get quantum computing to do something useful for computational science. It's late in the afternoon, you've had a whole week of training, so I'm going to go easy on the tricky concepts, and there'll be some references later if you want to follow things up. But let's just step back a bit and think about why we might be interested in quantum computing. Often one of the main reasons why we should be so interested is given as we're expecting quantum simulation of quantum systems to be among the first useful applications of quantum computing. But that really depends who's doing classical simulation of those systems now, who might need a quantum speed up. So here's a nice infographic of the world's supercomputers. And you can go and get all sorts of versions of it here if you like. So that's the UK's share of the world's supercomputers currently. It's shrunk since I did the last one. But everything jumps around on this graph depending on who got the most recent big one. And it's Japan in this case, so they've increased their share massively with this big spot here. This is a picture of Titan, which is one of the ones in the US's spot. I'm not quite sure if I can see which one it is. They're not labeled quite right. Anyway, but what they do, well, one thing you know what they do. They do molecular dynamics, for example, simulating biomolecules, what you've been learning about doing the whole week. They monitor pandemics. So this slide I originally wrote before COVID-19 came along. But they've been modeling pandemics for many years. Swine flu was the most recent example when I wrote the slide. So simulating the human body in all sorts of detail from the molecular processes on up to the physical processes. Designing quantum materials. Weather and climate forecasting is a big one. And that's one of the big blobs in here for the UK is the Met Office computers. Simulating nuclear explosions, because it's generally not a good idea to study the real thing. And there are, of course, a bunch of other things the supercomputers are churning away on that they don't tell us quite so much about. But that's already a very interesting list, quite a bit of which you'd like to be doing. But supercomputers tend to be these huge rooms full of racks and racks of computers, and they take a lot of power, and there is a limit to how big we can make them in terms of how big computations we can do. So that, if you like, is the goal of thinking about quantum computing. We already have very powerful current computers currently, but there are barriers to making them more powerful. And essentially one of them is that the current silicon chip technology has reached its limits. I've got a picture of that on the next slide, I think. And the other is that energy consumption. It's actually far from optimal in this design of computer. There's a lot of room to improve there, and there are other hardware designs that are more energy efficient. But that's not this talk, but it's something to think about in terms of global warming and climate change. There's a significant fraction of the world's energy use does go on computers in general and supercomputers in particular. And there is a relationship between these limits, and that's the physics of silicon chips. So silicon as a material has a heat conductivity, and you can't cool them any faster. You just can't conduct the heat out any faster, the heat that's produced when they're used to compute. So there's the graph that shows you this happening by proxy. So this is, these two conveniently fit on the same number scale here, but we've got the number of transistors in black in per cubic millimeter, I think it is, I can't remember exactly. And the speed in hertz in blue, so that's how many operations per second they're doing. And then in this one, on the other scale, is the feature size in meters. So down we go here with some little jumps in the places. And you see that one keeps going down. We're heading down towards 11 nanometers and then down towards 9 or 7, the feature size that they're etching. And you can see this one has kind of gone up to this point too, but this one has tailed off. It's not growing exponentially anymore. So even if you make the feature size smaller, pack more transistors in, you're still not getting faster because you can't cool. So Moore's law, this is an original Moore's law graph from the Intel website. Moore's law stopped in the early 2000s, somewhere in here. So of course they're still making lots of chips, but they're now making specialized chips. So you name it, they sell a chip for you. Your mobile phone, your toaster, your self-driving car, a rugged version if you want to send it into a volcano or onto the moon, they've got a chip for you. There are dozens, if not hundreds of specialized chips now. Whereas down here, you named each spot on here had its name. They were making one kind of chip as we moved up this here. So what's happening is the future is diversifying. And we're getting different types of computational device. We're networking different types together. We're getting embodied computing, distributed computing, multi-core's been with us for ages, and we're optimizing for the particular task. And of course, we're looking beyond silicon. So this is a page full of the crazy stuff that's going on out there. Not so crazy, maybe the IBM quantum computing chips. That's a 16-qubit one. That's a hybrid with real neurons on silicon, so they can exchange signals. That's a chemical reaction, which is very pretty, but quite slow for computing. But chemical reactions is in the running for looking for alternative computing hardware, not in a Petri dish quite like this. This is a reservoir computer. It's basically a lump of resin and carbon nanotubes munged together with a lot of electrodes in it. And it behaves more like an analog computer in that you put a set of inputs and you get a different set of outputs weighted. So it's kind of like a neural net, but except you don't design it, you just take however the nanotubes came in there. You can encode in DNA, that's just an example encoding, and you can get slime mold to compute for you. I'll leave you to look that one up if you're interested. So future computing is getting very diverse. And if we want to use this stuff, we're going to need to co-design the algorithms with the hardware. Because how you're going to program a lump of carbon nanotubes or a chemical reaction or a rat neuron, never mind the quantum computer, is going to look very different from how you're programming the computers you've just been learning about. So let's think about this hybrid idea a bit more carefully. So this is what we do in practice. So conventionally, you'll have graphics cards. They've been with us for decades. Field programmable gate arrays or application-specific integrated circuits that are more efficient than a general purpose one. All of these are things you might find in a well-appointed high-performance computing facility these days. So this is the norm in practice for what you're expected to be able to use to run your programs. And unconventional computing comes in much the same format, really. You have your classical computers that are your way in and your way to control them, but then you might have a quantum chip. You can do computing with an NMR setup. That's the reservoir computing from, and there's the slime mold from the previous page, for example. And that's all fine, except that the theory of how we compute is single paradigm. So we've got a nice theory of how classical computers work called a Turing machine that looks nothing like your silicon computers that you use, except that you can map the theory between them and understand how they work. If you want to do analog computing, there's something called Shannon's GPAC in terms of the theory. Quantum has a whole bunch of different models. I'll explain what some of these are. That's a quantum Turing machine, so the quantum version of this. And there are even other computational models that are not equivalent to these ones. But again, you have a whole theory of this, but you have a theory by itself. What you don't have is a good theory for how you link them up as co-processors. So a lot of this is more experimental, the way we're setting it up. It's quite clear that we're going to want to do high performance computing with the option to call a quantum coprocessor, but nobody's done the theory that way yet, or they're only just beginning to think in practice how to do that. So let's just be clear we understand what we're doing when we're doing simulation. So what we simulate on a computer is a mathematical model. It's not an actual physical system or biological system or molecule or whatever. It's the model you are making of that physical thing. And so where computational science sits in this, it looks something like this. This is a diagram I drew a long time ago, just to kind of show the information flow of how we make our mathematical models. So where we can do analytical calculations, or great, then we can do experiments and we can compare our model predictions here with the experiment. But we often can't do analytical calculation because our model is too complicated for that. So then we can try doing some numerical simulations. And again, they won't be perfect because we'll have to do finite precision and we might have to make some simplifications to get the numerical simulation to work. But we can compare all of these things, see how well they match up, and revise our model and repeat it and see how we go. So computational science is testing the models when we can't test directly with analytical calculations. So for scientific modeling, this is what we're doing with our models, is creating a description of something that we hope is accurate enough to let us understand the real world that's out there. So this is a slide from my outreach talks, but it's the pretty version, but there is a whole article on this that you can go and look up. It's a very interdisciplinary article, and it's all in diagrams, not equations. So it's certainly understandable. It's not like you need to know anything technical. And that's looking at the computing process here and saying, well, what is it that you're doing when you're doing a computation? So you have a problem, and you might be that you want to model a physical system, but it might be that you want to solve something else. It might be as simple as working out your taxes for the year, or it might be much more esoteric. You might want to test a mathematical conjecture and want to try out some examples. You might want to check whether numbers are prime. It could be almost anything. But the problem doesn't look anything like a computer, right? The first thing you need to do is to figure out how to encode it in a way that you can actually programming into the computer and get the computer to help you solve it. So the computer will then do something, it'll run, so some dynamics will happen, it will change its state, and then you'll get some output. And then you'll do a reverse process where you take the output in computer language and turn it back into the same language that your problem is in, and then see what result you've got. So you can see there's a flow through here like this. As on the next slide, I think I should have a flattened version of that for quantum computing. There we go. So there's the input. So in a sense, what you're trying to solve, the problem you want to solve, is not related to the quantum computer you're going to use to solve it. So you need to do some encoding. And that funny thing in a bracket is the way we write a quantum state as an input. We then need to evolve it. So that's our run the program, make the computation happen. We get an output that's a different state from the input. And then we'll do that decode process again to get our result. So you can see that what we've done here is we've put a quantum system in where we had the classical computer in the process here, but otherwise it looks exactly the same. So this, in quantum mechanics terms, what this type of evolution has to follow the laws of quantum mechanics, which will mean it's unitary evolution in mathematical terms. More generally, you can have an open system, a noisy environment one, but I can deal with that by making the size of the whole thing larger so it includes the environment that it's connected up to. And you can do this with a gate sequence, a sequence of instructions much like you would on a classical computer, or you can engineer the quantum Hamiltonian such that when you apply it for a time, so it's time dependent, and we apply it for a time t, so we're integrating over time, applying it to the input state, that's a time ordering thing because we're saying that things don't commute here. We've got matrices basically, the order you do things in matters, and there's our output state. So that's just the quantum equation way of writing what I wrote there, saying take my input, apply my unitary evolution to it, and I get my output. So this picture, it covers most of quantum information processing, in fact, including communications, because what you're trying to do with communications is get your message, your input, to your output without getting it corrupted in any way. So you might, the simplest way you can think about sending a message, right, is posting a letter, and you hope it doesn't get lost in the post. So your aim is that the letter arrives the other end still in a way that you can read it. Well, kind of the same thing here. If the channel it's got to travel through is noisy, it's non-trivial whether the state's going to arrive at this end without being corrupted. But one last thing in this sort of step back way of looking at things, these encode and decode steps have arbitrary choices in them. There's different ways you can encode your problem into your computer. And in the quantum case, you can see that very simply. If we're using a spin up and spin down as two states, we can choose which one represents a 0 and which one represents a 1. And so long as we do that consistently all the way through this process, it doesn't matter. So that's not a quantum thing, this encode and decode. It applies to classical computing too. You choose what you, how you represent this unrelated problem you have in the physical characteristics of your computer. So I'm going into some of this because if you're used to thinking of a computer as the thing you've always had, your phone and your laptop, and then the sort of thing in the machine room in the back, and you think computers just work this one way, it helps, if you want to then put a new kind of computational device in there, it helps to have thought a bit more generally about what it means, what it is that makes it a computation, and how to put the pieces together. So this is my one slide to understand why you might get something really interesting out of a quantum processor that you can't get out of a classical one. So the whole of quantum information, including quantum computing, is built on the idea that quantum logic allows some tasks to be done more efficiently than classical logic. So if we think of a classical logic in which we have bits or true, false, what happens in quantum is you can have a superposition of the 0 and the 1, the true and the false, with complex phases. This alpha and beta are complex numbers here. And so you get binary decisions here, yes and no. Here you get the yes and the no, the 0 and the 1, but you can get the superposition of them. And something else which for computational people often resonates, in classical logic, if you want a random number, you get a 0 or 1, heads or tails. In quantum, you get random numbers as part of the system. When you measure something, if it was in one of these superpositions, that can give you a random number there, right there, as part of the way the system works. Whereas you have generating a good set of random numbers is computationally hard. If you use pseudo-random numbers, you can spend a lot of compute time generating them. And if you need them for doing a Monte Carlo simulation or something, you have to budget your time for doing that. Whereas quantum, we can get randomness intrinsically built into the system. So if it's a different logic, it's not necessarily a big surprise that you might get some different computational power out of it. And the question is how different between these two. And so computer scientists think of this term, they think computability is what you can compute, theoretically at least. And complexity is how efficiently you can compute this. And so what we think, and not all of this has a watertight proof, is that the computability questions, quantum and classical, are the same. So what is possible to compute, some things are uncomputable, doesn't change when you put quantum logic in there, but the complexity does differ. And some problems can be computed more efficiently classically. So then the question is where, and are any of them my biomolecular simulations? Well, quite possibly. But let's just go back to that encoding for a second to explain just in more concrete terms why I've said it's important. So if we have a number, this is a unary representation of it. So 4 is represented by 4 spots here. And so n by n spots. So when I do my binary representation of it, you notice I need less bits than spots. I only need log to base 2 of the n number of bits instead of having n here. So that's an exponential difference, log exponential. It's better for precision because you're measuring bits and you just add another bit, and you're still measuring is it 0 or 1, but it's doubling your precision there. And it reduces the amount of memory you need. So this again is not a quantum thing, but it got partly forgotten as people started to think about quantum computers, and they had to remember that some of the basic stuff to do with classical computing also matters. And notice that floating point gives you an even more efficient encoding, because now we have another piece here that's giving you a log factor in order to represent very large and very small numbers. But you're trading precision here because you haven't got 89 bits of precision here. You've got whatever your machine precision is. And of course, you have to be quite careful if you're subtracting numbers that are nearly equal and various other things that you get used to working out of your code if you have to write it at that level. But one reason to mention that is because, remember I said there were lots and lots of different ways that people are thinking about building quantum computers? So here's a picture of some of them. And it's sorted by how we've encoded the data and how we're doing the processing of the data. So binary, so digital encoding is the same as you'd use in a classical computer. And then discrete processing is gates, the same as you would think of classical computers doing it. And there's exactly a model of quantum computing that looks like that, except it's got those superpositions in it. And then there's another one that doesn't look anything like that, where you make a big quantum state, and then you measure all of the qubits in turn, and with the right order and in the right way, that will do your computation for you. Exactly equivalent to this. But there's also models in which you have a unary encoding. And the continuous variable boson sampling sits in here. These ones are interesting because we've got our efficient binary encoding, but we're doing that continuous Hamiltonian time processing. So this is the stuff that I work on, and I'm not going to really tell you any more about it, but just I want you to get the sense that as of now, we don't have one best way to build a quantum computer in one best physical system. Maybe IBM and Google would like you to think otherwise and think that their superconducting quantum computing chips are the only way to do it. But it's not true, and there's a bunch of people doing different things. I've got a list of a few later. And so just as we're getting a diversity of other ways to compute, neural networks or specialized hardware, quantum computing is not necessarily going to be one model of computing that sweeps everything else away. In future, we're likely to have diverse ways to compute, and it's going to be a question of figuring out which one fits your problem best and out of what's available. So if we're going to do quantum scale engineering, now that that chip size has got so small that it's almost quantum anyway, is it worth trying? So here's another slide to give you an idea of how a quantum computer is going to work and give you an advantage. This is another one out of my outreach talk. So it's doing it in pictures, which is a good way to do it for this time of a Friday afternoon. So here's our here are our numbers again, and here are our binary numbers. And supposing we want to compute a function for 8 different values, let's pick the first 7. So if we were doing this classically, we'd need to run our program 8 times, once for each of these values of x. And then we'll look at all of those 8 outputs and decide which one is the best, for example, and then we know which x we want to use. But supposing we could do all 8 values at once, well, that's one of the things that quantum mechanics lets you do. So I can make a state that has the 0, 1, 2, 3, 4, 5, 6, and 7, all in superposition. I'll need to normalize this. That's going to have a 1/2√2 there, but that's for just a part of the model. And then I can do my computation, compute f of x of this superposition of all of the inputs. And I'll get a superposition of all 8 answers. Okay, no free lunch. We don't get all 8 answers just out there in the list. We get them in a superposition. So then you need a clever program. And if you've got a clever program that can work with that superposition and figure out, say, which is the maximum, then you can get a quantum advantage. So a good algorithm is everything to getting an advantage, or a better program, even if it's classical. It's all about having a good method, a good algorithm. And the same is true for quantum. So here's some examples then of how we might build our quantum bids. As I said, there's many choices. Rydberg atoms, we can change the state of one of them and get a superposition of excitations in a cloud. These are nitrogen vacancy centers in diamond. We can put atoms in an egg box of a lattice. So the egg box is made of lasers, counter-propagating lasers. They're standing waves of light, and the atoms like to sit in the minima or the maxima. We can also make photons out of light, but we're going to have to keep it somewhere. So we trap it between mirrors. So there's 2 mirrors here, and then you can get a standing wave of light inside here. And you can do that a couple of ways. If you're doing it with microwaves, you can just kind of get the microwaves to leak in. But you can also trap an atom here, get it to emit into this mode of the standing wave, and then you'll have the light in the cavity and the atom sitting there in its ground state. So that's again a way of doing the equation on that. So nothing in the cavity and the atom in an excited state, or the atom in its ground state and one excitation bouncing around in the cavity. And it's quantum, so of course you get a superposition of this. And this is real experimental apparatus. These are experiments that people do in labs and have been doing for a couple of decades. It's beautiful stuff, and very, very clever experiments to get this to work. We can also not bother to trap the photons, but send them through waveguides. So these are etched paths through a piece of glass. You can use laser to etch the paths. And then you can send the light in here. And where it goes through something like this, it's like a beam splitter or a phase shifter. And then you'll get a pattern of where it comes out that you can measure. And that's the result of your computation. So these pictures are from Bristol, where for a while they had these online, and you could actually send a program to it of photons and it would run it and tell you the output. But it's not online anymore, I don't think. So who is actually building more serious quantum computers? I've shown you experiments now. And so the answer is lots of universities and research centers are doing hardware and software. But also there are many companies, and notably the ones that have hardware now that they're talking about. So IBM, Google, and Rigetti are building superconducting qubits. So they're they're etching them in not silicon chips, but they're like silicon chips, and they look quite like silicon chips. They're just different semiconductor materials they're etched from. And they look something like this. So this is the IBM 7-qubit chip. So what you've got are these zigzag things are microwave resonators. And so they're zigzag because microwaves are huge. So they have wavelengths around centimeters. And if you need a resonator, it's got to be about that size for a microwave. So each of these is a microwave resonator or coupler. And then these things are the 7 chips, qubits on here. And this is a magnified picture, okay, but not by much. You can still see these qubits with the naked eye if you have that chip. You know, it's like a 2 centimeter square chip, roughly. So we're at the scale of this sort of chip, we're in the days when we could still see classical bits, which I will admit to being able to remember. I have actually seen classical bits in memory, in core, little tiny copper rings with cross wires so that you could read them out, little tiny copper magnet rings like magnets. But that was kind of like 60s, early 70s. So this is in a way where we are with the rate of hardware development. We're early days, pioneering. What we've got on this list that I skipped over, so what D-Wave have done, they've actually built superconducting qubits that are much smaller than this, and you definitely can't see with the naked eye. They're packing 2,000 to 5,000 on a chip that is maybe a half a square centimeter. But one reason why they've made them so big to start with is it makes them less noisy. So the D-Wave ones are noisy, and they're cooked up in a way that is going to do a continuous time processing that's not quite as powerful as eventually ones like this might be. So what IonQ are doing, they're making ion traps like that egg box I showed, or just with other kinds of electrodes. And they can trap maybe 100 ions with very high fidelity in there currently. IBM, Google, Rigetti, there may be 65, maybe more qubits now in that kind of space. So they're getting better at engineering them. PsiQuantum, which was co-founded by people out of Bristol who've moved to Palo Alto, they won't admit what they've got yet, but they're using photons. So they're doing the version like this that is all photonic. So that's what we know about with hardware. And as I say, there's comparable research going on in universities across the world. Often they're solving particular engineering problems rather than building whole chips that compete with the ones that the companies are doing. So, okay, what could we do with 65 qubits? Well, first I'll tell you what we can't do with 65 qubits. And that's the factoring problem, because that's maybe the one that you've heard of, that quantum computers will be able to do faster than classical. And it's the basis of crypto schemes. It's the basis of the RSA of cryptography that is widely used to protect data, for example, for banks or financial security. And it's true that a large enough computer can run Shor's algorithm and break when you're given a number that's actually got 2 prime factors like this, it will be able to find them. So again, in one slide, this is how it works. You put your number in, and you put another number in that's co-prime, and it's easy to check that. Euclid's algorithm will check that efficiently. So this is a bit of classical number theory to make sure your inputs are right. You prepare a huge quantum state using these 2. And then what you'd like to do is find the periodicity of this state. And of course, the Fourier transformers, that's what they're good at. They find periodic structures in things. And what you can do with this quantum state here is apply a quantum Fourier transform more efficiently than you can do classically. Then you measure part of the state. You do some classical post-processing that's efficient, and with a high probability, you'll spit out one of these factors after that. What you're trying to do is find the periodicity of x. X is that input that's all possible numbers, remember? Raised to the power of this coprime. But then instead of just getting that bigger and bigger and bigger, as x gets bigger, you truncate it mod n. And so that's where the n gets input into this. And then once you've got your r out of here from the measurement, this a to the power r over 2 plus or minus 1 will give you a factor of n with high probability. And if it does, you don't get one the first time, you just try it again or try another a. And after a few attempts, you'll get there. So great, we've got an algorithm. However, what does it take to beat classical? Remember those big roomfuls of classical computers? Right, the best classical, I haven't checked this recently, but it's not going to get much better because it took months to crack this one. 232 decimal digits, 768 bits. That's what classical has done. So you've got to do better than that to be worth doing quantum. So we're going to need 2n qubits in the QFT register, 5n for the modular exponentiation. So that's 7n qubits. N is our 768 here. So we're going to need 5,376 logical qubits. Okay, that's kind of a couple orders of magnitude more than we've got today. But now we're going to need some error correction because we've got to do this pretty accurately. And then it blows up 2,200 times, maybe 10 to the 5 times this 5376 number. So we've got a better scaling. So this is the number of bits and how long it will take, the number of logical bits and how fast the computer's running. And this is what happens classically, is you get this very, very steep curve. So you cross, but the crossover point is high. It will probably need a teraqubit quantum computer. This is not the first thing we're going to do usefully with a quantum computer. But if you want to simulate a quantum system, so maybe the electronic structure calculations that you need to input into your biomolecular simulations, they're hard because fermions are awkward and they need you to make them antisymmetric, and that's hard to track in a classical simulation. There are ways, but it's not the easiest thing to do. And just generally, if you've got n two-state particles, you want to keep track of 2 to the n possible states. It could be in a superposition of all of them. But now if you look what classical needs, one complex number times the size of a double, a terabyte will get you n is about 36. And if you add another one, you double that to 70 in terms of so 37 needs 2 terabytes and so on. And so you can squeeze a bit more with some compression methods. People are pretty clever. They're up to maybe 64. But we're really pushing the classical limit if we want to do more than that. So if you simulate, someone says, oh, I'm simulating hundreds of quantum particles. Great, but they're doing it in a subspace that is probably not larger than this. So you can't simulate it in its full generality. So that is a pretty hard limit on what you can do classically because of this doubling thing. And that's where we think that quantum systems will come in first, quantum computers. So how are we going to get there? This is where CCP stepped up and said, we're not going to get there if we don't work together with the computational scientists who already have the cutting edge code and know where the hard problems are and exactly what it is they need, they want to speed up. So the idea of CCP-QC is that we're working with people like you, And we're bringing you together with the quantum scientists and engineers who know how the quantum computers work, but don't know all the details about the problems that they want to apply them to. But together we can develop the first useful applications. So we've got lots of key partners in the UK. We've got the computing consortia, as well as the CCPs, the National Quantum Computing Centre, which his website is up recently, the UK Hub for Quantum Computing and Simulation, which is doing a bunch of science and engineering towards developing quantum computers. The national labs are on board, and there's a bunch of software startups, so there's some extra help in how to do the quantum programming. So what we're planning to do, well, we're a network like CCP-BioSim, so we want to organize joint meetings with CCPs and invite the quantum computing community, especially early career researchers, so that you can collaborate and do some really solid development towards quantum computing applications. We plan to run trainings to teach more details about quantum computing. It's a Friday afternoon. I'm not trying to teach you everything you need to know in 1 hour talk. But we're running small projects to develop proof of principle code and demonstrations on early quantum computing hardware. So that 65 qubit Google or IBM chip might not be enough to do something useful yet, because it may be too limited from the noise or the way it's connected. It may not run the algorithm you need just yet. But maybe we can run a small one and show that it will work once we've got double or treble the number of qubits. And then we'll know where we're going and where we're heading for. We're developing an online information resource on our website. There's a bunch of talks there on various aspects of quantum computing that you can go and check out if you'd like. I've also written recently an equation-free introduction to quantum computing. This is going into an interface focus special issue, open access, but you can read it on the version on the archive now. So that it tells you more about the continuous time stuff that I do, but in a setting that makes sense to life scientists. That's the aim for this audience, is people who are not ready to look at the quantum physics yet, but they still want a fairly accurate way of understanding what quantum computing is and might be able to do. Well, let me tell you a little bit more about the projects we're doing. We've actually completed the first one, and that's a survey of methods for quantum enhancing computational chemistry applications. So there's been a lot of hype and a lot of papers on this, and a lot of what's being done is essentially a slightly quantum version of a neural network to search for a good input state or a good solution state to the problem. It's not clear this is going to give us a true quantum speed up yet, but it might be able to search faster than a classical neural network. But on the other hand, as I keep saying, we've got very powerful classical computers, and there's nothing that they've done quantumly yet that you can't just as well do in a classical computer for the minute. But the methods themselves are interesting. So we're going to be doing a few more projects. One is, so you can see the range of areas that we might end up with a quantum speed up. So smooth particle hydrodynamics simulates a continuum, or more or less continuum model, with many discrete masses, but they're soft and they're following a Hamiltonian evolution. So mapping them to a quantum processor, there's a natural Hamiltonian correspondence here that we want to see if we can make work to get a speed up. So that's planetary collisions there, but you could just as well be modeling something that's a fluid flow on a much smaller scale. Electronic structure calculations. CASTEP is an example of software supported by CCPs that would be very interesting to put a quantum subroutine in for the energy minimization step. And it's done exciting things like predicting a new hydrocarbon. The next one we're going to run is actually this one. It's an optimization problem. And it's a little closer to home maybe for you guys. Macromolecular crystallography. So if you've got a complicated molecule, but you can crystallize it and do X-ray diffraction on it, you've then got a whole bunch of data that you need to back out the structure from. And you've got amplitudes, but not phases. So you need to do an optimization with the phases in order to find out the best fit for the structure. And this is really would match onto qubits well, because it's an angle. So the 0, 1 or something in between is exactly what you can do with a qubit. So this is what we're going to look at, is whether we can come up with a good quantum algorithm for doing the phase optimization for this. And there will be other projects that the CCP communities suggest. So these run by forming a working group of people interested. So we bring expertise from the CCPs and the quantum community to sit down in a small enough group to really work on the details, exactly like you'd expect research collaboration to work. So here's just to wrap up now, as we're getting towards the end, a list just so you can see. Your very own Sarah Harris is firmly in helping us to run CCP-QC. And this tells you, you may recognize a few other names in the list there if you've come across people. And Alan gave you a talk earlier about electronic structure calculations. So a little bit more step back. The context is, for when are we going to get a quantum computer? Well, things are moving quite quickly. So the big investment started about 2014. We've had 5 years of the hubs running on imaging, metrology, communications, and computing. We then got another 80 million into the hubs so that they could continue the work and the spin-outs, and a lot more innovation funding. So a lot of money for companies to work with academics to develop the ideas further. And because computing is harder than the other areas, there's a National Quantum Computing Centre has been started. That's just the start of its funding. There's going to be a new building for it on the Harwell site. And that's where we expect there will be quantum computing hardware installed alongside small enough HPC that we can run our test algorithms with quantum coprocessors. It'll be a year or two before stuff is up and running, but it's firmly in the plans. There are big global investments going on in the EU, in the US, and China now is putting a huge amount of money into quantum technology. So there will be more startups, there will be many more interesting things, more hype and announcements, but it's a very exciting time to be working on this. So I'll leave this with the last slide. CCP-QC started right as lockdown hit. It's not so easy to start a network when you can't meet in person, but we're doing as many things as we can while we're online. There's a mailing list we can add you to. When we have joint meetings, you can present your work. You can attend training events, contribute to the projects as I've described. You can follow us on Twitter, visit the website, and we have a meeting planned for next year, hopefully in person, There's the website for it. And there's the link to the equation-free introduction article again. So thank you very much. I'm happy to take questions.
Thank you so much.